Okay, so let's do 12.3. So let r of t equal xt I plus yt j denote a position function. So if xt and yt are twice differentiable functions, then the velocity, which we'll denote by v of t, is defined to be the derivative of our position function. The acceleration is defined to be the derivative of velocity or second derivative of our position, and the speed is defined to be the magnitude of the velocity, or which is equal to magnitude of the derivative of position. Okay, let's look at a theorem now, theorem 6. Okay, so here's theorem 6. It says neglecting air resistance, the path of a projectile launched from an initial height h with initial velocity v0 equal to ai plus bj and angle theta is described by this guy here. So it's rt, so this would be the speed at time 0, cosine of the angle times ti plus h, which is the initial height, speed at time 0, sine of the angle t minus 1/2 gt squared, where g here denotes the acceleration of gravity. Okay, so we need to prove this statement here. Okay, so let's look at the proof of it now. So I'm going to erase a few things and start looking at the proof. Okay, so let's take a look at the proof. So again, here's a diagram of so it's a projectile that starts at a height h here and has initial velocity v0 and angle theta and is shot, say, and it's going to follow this path. So we have to find the equation. This path looks like it's following like a parabola shape. It's going to come down here. So notice here that the acceleration, during the acceleration on the projectile is the acceleration of gravity, and that's coming down here in the j direction. So therefore you can say here, note the acceleration to be negative g in the j direction. So it's coming down here. Okay, let's use that now to try and derive the equation. Okay, so let's now, I'm going to integrate the acceleration, get our velocity. So let's make an observation. So note then the acceleration is defined to be the derivative of velocity. So therefore we can find velocity by integrating acceleration. And my acceleration is negative negative gj. I can also write that like the following. So I can write that as 0i minus j direction. So let's integrate that down here now. Doing that, we get this. So we're going to be integrating the I component, integrating the j component. So integrating 0 is just a constant, and integrating g would be gt plus a constant. So let me write it here. So let's get a c1i and then minus gt plus c2. Okay, because integrating 0 becomes a constant. Integrating negative g become negative gt plus a constant. Okay, now let's note here that our velocity times 0 is ai plus bj. We're going to use that now to find the c1 and c2 values. So let's make an observation here. Okay, so again, our v0 is ai plus bj, but also from the formula we just obtained here, we have our velocity functions given by this. We can stick in 0 in place of t here then. That's how I got this. And now you can equate coefficients, so the a must be the c1 then, and the b must correspond to the c2 over here. Okay, so let's make that observation. Okay, so again, a then has to be c1 and b has to be c2. So therefore, replacing my c1 and c2 now with those values, my velocity function is going to be equal to ai plus negative gt plus b in the j direction. Okay, now to find the position, we can just integrate velocity. So let's do that. Okay, so next note that, as we mentioned already, the velocity is equal to derivative of position. Therefore, position will be the integral of velocity. And my velocity guys up here. So let's integrate the I and j components. Let me write down here. Okay, so we're going to integrate the a in the I direction and integrate this in the j direction. That should be j here. J direction here. So integrating a become at, integrating negative gt will become negative gt squared over 2, integrating b will become bt plus a constant, actually b plus a constant here also. So let me write the answer for these here. So integrating then, so again integrating the a become at plus a constant in the I direction, integrating minus gt will become minus gt squared over 2, integrating b will become bt plus a constant. Okay, now our job is to figure out the C3 and C4. But we know what now, at time 0, you're at H is your position, so let's note that. So note at time 0, for our picture or diagram up here, we're at H, and that's in the J direction, so you can think of at time 0 position is 0I plus Hj. Also, we can plug 0 into this equation we just derived over here. So let's write that here. So we get this because when you put 0 in place of t here, it just becomes C3. Put 0 in place of t here and here, it just becomes C4. So it looks like 0 has to equal C3, H has to equal C4. Okay, so again now our C3 is 0 and our C4 has to be 4. Sorry, H. So then our R of t then, plugging in up here with the C3 and C4 is going to be a t I direction, negative g t squared over 2 plus bt plus h j direction. So we're almost there now. We just need to get rid of the a and b's here. So we need to make an observation. So let's do that. Okay, I'm going to erase a few things here. Okay, so this is what we have so far. So we need to get rid of the a and b. Okay, so let's make some observations. So we're going to be looking at this little right triangle here. So let's look at the cosine of theta. So looking at the cosine of theta, it's adjacent over hypotenuse. So looking at this guy, the adjacent side to the angle would be a, and the hypotenuse would be the magnitude of my velocity times 0. So it'll be the speed at time 0. I can then solve for a here. Let's solve, so multiply both sides by magnitude of v0 or the speed at time 0. So let's do that. So we get this. We can replace the a then over here with this guy. Let's also now look at the the sine. So the sine is opposite of hypotenuse. The opposite side to be b over the speed at time 0. We can then solve for b. So multiplying both sides by speed at time 0, we get b equals speed at time 0 times sine of the angle. So we can make these substitutions now up here for b. We can substitute this guy. And for the a over here, we can substitute this. So let's make those substitutions. So making the substitutions for a and b, so substituting the trig functions, we get this then. And that's what we're trying to show in the theorem, so we're done. So this completes the proof. Okay, so we're done with theorem 6. Now let's take a look at an example. So let me erase some things here and write my example up here. Okay, so here's our example. So it's from practice quiz 2, number 3. It says a baseball player at second base throws a ball 90 feet to the player at first base. The ball is released at a point 5 feet above the ground with initial speed of 50 miles an hour with an angle of 15 degrees. So question, at what height does the player at first catch the ball? And we're going to use g, the gravity. It's going to be 32 feet per second squared because we have things in feet up here. Okay, so let's write down what we're given here. Okay, so we're going to use our theorem 6, our position function. Okay, and our h would be the 5 feet up here in our question. So h is 5. The angle is 15 degrees right here. And the initial speed is 50 miles an hour. That goes here. There's another observation. The 90 feet we haven't used that yet, so let me write what that would, what equation we'd use for that one. Okay, so the 90 feet part says the player at second base throws the ball 90 feet to the player at first base. So you can say he's throwing it at 5 feet. I drew a little diagram here. So he's 5 feet. He's throwing it to player. And the player is 90 feet away. Okay, so that's 90 feet in the x direction. And the x direction by our position functions, the speed at time 0 times cosine of the angle t. That's why I got this equation here. So the distance in the x direction would be 90. Okay, so we got this one also. Alright, so now we have to actually now change 50 miles an hour to feet per second. So let's do that. I'm going to erase this picture now. Okay, so we need to convert the 50 miles an hour to feet per second because we're given 90 feet here and we're given 5 feet. So all the other things are in feet, so we need to change to feet per second. So we got 50 miles in 1 hour. Well, there's 5,280 feet per 1 mile. So you can see the miles would cancel here then. You need feet per hour. So I want the hours to cancel. Well, 1 hour is 60 minutes. Then the hours would cancel here. And then I'm going to change that to seconds. So the minutes would cancel here. So if you did this multiplication, you get our feet per second. And let you check, it's roughly equal to 73.33 feet per second. Okay, that's what we're going to use up here actually for the our initial speed right here. Okay, let's keep going. Okay, so now I'm going to replace my 50 miles an hour now with 73.33 right here. So let me do that. Okay, I'll replace it up here now. Now let's look at this guy. Let me do it over here. So plugging into this now, the initial speed then is 73.33, then the angle is 15 degrees, and then t equals 90. We can then solve for t, so that's pretty much how long it's going to take the ball to get from the player at second base, from the player at second base to the player on first base. Okay, so let's solve this for t by dividing both sides by this guy here. So let's do that. Okay, so solving for t, we get 90 over 73.33 cosine of 15 degrees. Let you check, if you plug that in your calculator, it's roughly 1.27. That's going to be seconds or units here. Okay, so that's how long it takes to get from the player who threw it to the player who caught it. You want to see now how high the ball is when it's caught. So pretty much at what height does the player at first catch the ball? That's what our question up here. So we can plug into our J component. It should be a J on this. I forgot to write it on this. We can plug into our J component up here with our 1.27 as our T, and our G is 32, and our initial speed is 73.33. So we're going to plug into J component here with all our values. Okay, let's do that. Okay, so again we're looking for the height of the ball after 1.27 seconds. That's going to be a J component. So it'll be -1/2 G, which is 32, which I put here, times my time, which is 1.27, so it'll be 1.27 squared plugging into this, plus initial velocity, which is 73.33, times sine of the angle. The angle here is 15 degrees, times the time, which is 1.27, plus the initial height. Well, our initial height over here we said was 5, so 5 goes here. Okay, the 2 here, cross that and become a 16 up here. Then I'll let you check. If you plug this in your calculator, you should get the following. So plugging into your calculator, you can check it's roughly equal to 3.3 feet. Okay, so the player at first base catches the ball at 3.3 feet. Okay, so we're done with this example, and we're done with the section 2, so I'm going to leave the video here.